Hi everyone, and welcome to your fourth lesson in thermodynamics, where we are going to talk about the concept of entropy and spontaneity or spontaneous processes. So first of all, what does it mean? What is spontaneity? What does it mean to be a spontaneous process? Well, we've kind of shifted the language a little bit and to use the term thermodynamically favorable instead of spontaneous. And the reason why, now I take that back. That doesn't mean we don't still use the term spontaneous. So you'll see either or, but the reason there was a bit of a shift to using thermodynamically favorable is because the word spontaneous conjures up the idea of fast or unpredictable or out of the blue. And that isn't necessarily the case. So in chemistry, spontaneous process or a thermodynamically favorable process is a process that occurs naturally under certain conditions. In other words, it does not need any outside intervention. So it has a definite direction. It can be fast or slow. It's non-spontaneous in the reverse direction, and temperature and pressure are going to be major factors. So then, of course, if it's thermodynamically unfavorable or a non-spontaneous process, then it's not going to take place unless driven by an input of energy or taking away energy from an external source. So for example, let's think about an ice cube. If I set an ice cube out right here on the table, it's going to eventually melt. I don't have to do anything. Under the conditions of room temperature, that ice cube is going to go from solid to liquid. Now, it doesn't matter how long I sit here, it is not, thanks, aside, it is not going to go back into a solid ice cube unless I put it in the freezer. Then, under those conditions, it would go back into an ice cube. All right, so spontaneous or thermodynamically favorable means it's going to happen with no outside intervention. So I mentioned this in a previous lesson, but when we think about thermodynamics, it's easy to intertwine it with the idea of kinetics, when in reality, they involve two separate parts of a process. So thermodynamics is all about the beginning and the end. Where do we start and where do we finish? Kinetics is that pathway. How fast does it happen and what steps does it go through? So to say something is thermodynamically favorable does not mean it is fast. So for example, nuclear decay. There are some radioactive isotopes like TC99 that decays in a matter of days, whereas something like uranium takes years and years and years, but both of them are a naturally occurring process. Another example is diamond will actually turn into graphite. If you weren't aware, diamond and graphite are both just structures of carbon. They're just in different forms. But my ring is not going to turn into graphite by next week. All right, it would take millions of years. So even though it's a naturally occurring process that doesn't require any outside intervention, it takes millions of years. So thermodynamically favorable doesn't always indicate speed. In reality, if all you know is that it's favorable or not favorable, then you know nothing about the speed. The only way you know anything about the rate is to be given kinetic information. So just don't confuse those two things. So then where does this concept of spontaneity or spontaneous come from? What does that mean? So we can think of a flask that has gas on one side of it. And right now, on the left-hand side, this valve is closed. So all the gas is over here in the left chamber. If I open that valve, spontaneously, it's all going to spread out. The gas is going to take up both sides of the container. You don't have to do anything to make the gas do that. So then it is non-spontaneous that all the gas particles are going to pack themselves back into that individual one left bulb, right? So it's spontaneous for them to spread out. Another example, we've been talking about how when two objects are put together, heat flows from the warmer object to the cooler object until they're in direct equilibrium. That is not something that we have to make happen. That's a spontaneous process. It's just going to happen on its own because energy likes to be dispersed. Well, we can't really personify molecules and energy, right? It's not what they like or they dislike. So where this actually comes from is a probability. So let's look at this example. So entropy, by definition, is a measure of molecular randomness or disorder. So entropy is what can drive spontaneity, and it deals with this idea of probability. So let's think about if we have two particles. There are 4 total arrangements for these 2 particles. They could all be in the right bulb, they can be in both, they can flip-flop but still be in both, or they can all be in the left. So it is a 50% chance that there's going to be an even distribution. In other words, they're more spread out, they're more disordered rather than being together in one side. Now let's up that. Let's say we have 4 particles. Now there are 16 total arrangements, but the highest probability is to find an arrangement where they are the most disordered. So entropy, this idea of disorder, actually comes from probability. It comes from the most probable state is that they are the most disordered. I kind of like to think of them like toddlers. Chances of a group of 16 toddlers being all nice and neatly lined up in the corner of the room is very low. The chances of all 16 of them being crazy dispersed across the entire room, much higher. So disorder, chaos, randomness, that's favored because it's most probable. So when we think of our states of matter, entropy is going to increase as a solid becomes a liquid and becomes a gas. Or if we had like a reaction that had all gases, then we're going to have more entropy the more gas molecules that we have. Okay, so we've got to think of it on the molecular level. The molecules have more and more disorder, more and more energy to be dispersed throughout as we change from a solid to a liquid to a gas. So I've given you 4 reactions or physical changes, and one of the things that you need to be able to do is you need to be able to predict the sign of the change in entropy. Now, this was written on the previous slide, but I didn't point it out. So a negative delta S means a decrease in entropy, and then a positive delta S is an increase in entropy. So for this first one, we have solid sodium nitrate dissolving into aqueous sodium and nitrate ions. So if we think about it, if we have a solid versus the ions being dispersed in a solution, that is absolutely going to be a positive change in entropy. Freezing of liquid water. So we're going from a liquid to a solid. We're going to decrease our disorder, so that is a decrease in entropy. Going from solid carbon dioxide to gaseous carbon dioxide, that is absolutely going to increase our disorders. That is an increase in entropy. And then calcium carbon monoxide decomposing into calcium oxide and carbon dioxide. So if we look in the reactants, it's all solid, but in the products, we have a solid and now we have gas. So we are going to increase in our entropy. So far, we have been talking about the change in entropy for a system itself. Now let's think about the change in entropy to the surroundings. So the change in entropy of the surroundings is going to depend on change in enthalpy and temperature. Now, why do we have this negative sign right here? That's because we need to flip it in order to be in the perspective of the surroundings. What do I mean by that? So if we have a system and it's an exothermic process, it is releasing heat, right? And so what does that mean for the surroundings? That means the surroundings are absorbing that heat. So in the perspective of the surroundings, it would be a positive delta H. And so that's why we have that negative there. Vice versa, if the system itself is absorbing heat, then that means that the surroundings are losing heat. So we have to flip the sign. So why is temperature a factor? Let's think about it. Depending on what the temperature of the surroundings are is going to dictate how much an increase or a loss of energy is going to affect it. So I have this $100 bill here because for some reason, I still clear as day remember in a chemistry lecture in college, my chemistry professor teaching this concept, and he talked about, okay, think about a $100 bill. If you hand a $100 bill to a broke college student, that's huge. That's like multiple cases of beer, or that's like 10 trips to Chipotle. Like a $100 bill goes a long way. But if you hand a $100 bill to Bill Gates, like he would drop that on the side of the street and not even notice, right? So if you have a very, 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 very low temperature in your surroundings, maybe a little bit of heat is going to do a lot. But if you have a huge high temperature of your surroundings and you add a few more kilojoules, who cares? So temperature is going to play a factor in this idea of entropy change. So far we have had standard enthalpy of formation, or standard enthalpies in general. Now we're going to look at standard entropies. Same idea, delta S, the degree symbol means it's at standard state, so 1 mole at standard temperature and pressure. And with those values, we can calculate the change in entropy for any reaction using the individual entropy values of the reactants and the products multiplied by their coefficients. So if you notice, this equation, which is given to you on your equation sheet, looks exactly like the delta H equation. It's just using entropy values to calculate change in entropy. All right, so for example, here we're asked to calculate the change in entropy for the reaction given the standard enthalpy values. Now, something I didn't mention last slide were the units for entropy. They're joules per mole Kelvin. So a couple things to note. We're usually given entropy in joules, not kilojoules. A lot of times enthalpy is in kilojoules, so you got to pay attention to that. And then the other thing is we have mole Kelvin. So remember I said temperature dictates entropy. So that's why that Kelvin, the temperature is included. Okay, so the change in entropy is equal to products minus reactants. So 2 times 248 plus 2 times 38. Those are my products. Minus my reactants, 2 times 53 plus 3 times 205. And when I do that math, I get negative 149 joules per mole Kelvin, which indicates to me that there was a decrease in entropy. And sometimes I can look for a common sense check. And in fact, I did go from 3 gas molecules to 2 gas molecules, so I did expect it to be a decrease in entropy, which it was. Okay, so we've now learned about enthalpy, delta H, and entropy, delta S. Now, what scientists have done is they've combined those two variables in an equation to calculate what we call Gibbs free energy. And by definition, Gibbs free energy is energy available as useful work. It is in kilojoules per mole. So I'm going to go ahead and point this out to you because it is so annoying and tricky. Oftentimes, delta H is in kilojoules and delta S is in joules. And then delta G is usually in kilojoules. So a lot of times you need to convert your entropy value, okay? So I'm just going ahead and putting that out there now. So what Gibbs free energy does is actually give us a numerical value to determine if a process is spontaneous or not. So it's going to relate enthalpy, temperature, and entropy. Now that T, remember entropy is in joules per mole Kelvin, the temperature is in Kelvin, and that's what's always positive, right? We can't have negative Kelvin, and so we don't need a negative temperature to affect our signs here. So again, we're using this to predict spontaneity. If delta G is negative, then the process is spontaneous. If delta G is positive, then it is non-spontaneous. If delta G were to equal 0, then we would be at equilibrium. We wouldn't be proceeding forward or reverse. So, for example, we have solid water to liquid water. My delta S value is 22.1 joules per Kelvin mole. My enthalpy value is 6,030 joules per mole. So this time I do have both of them in joules. So this asks me to calculate delta G at 10 degrees and delta G at negative 10 degrees. So the equation, which is again given to you on your equation sheet, whoops, that's not what I meant. So this equation right here, (6030) minus 10 degrees Celsius is 283 Kelvin. And then my delta S value is 22.1. When I do that math, I get negative 224.3 joules per mole. Again, both of them were reported in joules, so then my answer is in joules. Notice because I multiplied temperature, I lost that Kelvin. Now I'm going to do the same equation, but I'm going to do it at negative 10. So I have 6030 minus 263 times 22.1. This time I get positive 217.7. Now, this is a perfect example of where temperature actually dictates whether this process is spontaneous or not. Because at 283, we get a negative delta G, which means that it is a spontaneous process. So in other words, if the temperature is 283, this reaction is going to happen. The solid will melt. Now, that makes sense to us because 10 degrees Celsius is above freezing. But if you look below, when we were at negative 10, we got a positive delta G, so it is non-spontaneous. So spontaneity is temperature dependent. So let's look at this example. What this does is this puts all of our possible combinations together. So as a reminder, our equation is delta G equals delta H minus T delta S. Now, there is a set of conditions where no matter what, it will always be spontaneous. And that's this set right here. Because when we have a negative, we have a negative delta H minus T times a increase in entropy. A negative minus a positive will always and forever be a negative. So the favored condition, the always spontaneous condition, is an exothermic reaction that increases in entropy. That is always spontaneous. That is what is favored by the universe. Okay? Now, there's also a set of conditions where it is never spontaneous. And that is when we have the opposite. When we have an endothermic reaction and a decrease in entropy. that is forever and always going to give me a positive delta G, because we're going to have a positive number minus a negative, which means you add it. So we'll always, always, always be positive. Now, our other two options, those depend on temperature. So if I have, let me erase these. If I have an endothermic reaction, but an increase in entropy. So endothermic is not favored, but an increase in entropy is favored. What I got to think about is what will give this a negative delta G? Well, this term right here needs to be larger than this term to give us a negative sign. When will that be large? High temperatures. So if it is endothermic but an increase in entropy, it is going to be spontaneous at high temperatures. Now let's look at the other combination. We have an exothermic reaction, but a decrease in entropy. So we have a negative number that is going to then be added to something. So for this to be a negative delta G value, we need the enthalpy term to be greater than the entropy. So then when is that going to happen? When T is very small, so low temperatures. All right, so then if a process with this combination is right here, if that process is spontaneous, then we say that it is entropy driven, because it's the entropy value that was the favorable condition. If this combination is in fact spontaneous, then we call it enthalpy driven, because it was the delta H value that was the favored. Okay, so knowing all of this information, we can determine what temperature a process will become spontaneous, or what temperature it will be spontaneous. So, AKA, when will delta G be less than 0? Okay, so I can set this up like an inequality. I can say delta G is less than 0, so 0 is greater than delta H minus T delta S. So I just plugged in the equation there. Okay, so 0 is greater than 31 minus T. Notice we're joules, kilojoules, so I'm going to convert this to kilojoules. 0.093. So then I have 0.093 times temperature is greater than 31. When I divide, I get that temperature. So this is going to be spontaneous when the temperature is greater than 333 Kelvin. And remember, so this is a positive delta H and a positive delta S. Positive delta H is not favored, positive delta S is. So if asked, we would say that this is entropy driven. All right, another example, estimate the temperature at which the below reaction stops being product favored. Now, product favored is just another way of saying spontaneous, okay? So stop being spontaneous, then we need delta G to be positive, so greater than 0. So then we're going to say that 0 is less than delta H minus T delta S. So 0 is less than negative 847.6 minus T, I'm going to change this to kilojoules, negative 0.0413. So I end up with 847.6 is less than positive, because negative and negative make a positive, 0.0413 T. And so T is greater than 20523 Kelvin. So that is a massively high temperature, but at that point, it would no longer be spontaneous. So anytime the temperature is greater than 20,523 Kelvin. And so here, exothermic is favored, but a decrease in entropy is not favored. So we would call this enthalpy driven. All right, so just like we talked about that we can calculate the change in enthalpy for a reaction given individual enthalpy values, we can calculate the change in entropy for a reaction given individual entropy values, we can calculate the Gibbs free energy of a reaction given Gibbs free energy values. So for example, down here, we're asked to find the delta G of the formation of ammonia. And then we're given the delta G values. Now notice here for nitrogen and hydrogen, they are 0. And that's because they are in their natural state. But the equation for this looks just like the other two. And it's going to be, we're going to take the values, multiply by their coefficients, and it's products minus reactants. So for products, we have 2 times 16.5. Oops, sorry guys, that was a typo. This should be negative 16.5. So 2 times negative 16.5. And then we would do minus our reactants, but in this case, it's 0 plus 3 times 0. So the delta G would be 2 times negative 16.5, which is 33 kilojoules. So this is a spontaneous process at standard state. So now let's kind of put all of this together. We're going to calculate delta G of this reaction. Now remember, our equation is delta G equals delta H minus T delta S. Well, we aren't given delta H or delta S. Instead, we are given individual heats of formation and individual entropy values. Given those, we've got to first calculate delta H and calculate delta S to then plug them in with the temperature into this equation. So I'm going to start with delta H, products minus reactants. So 2 times negative 396 minus 2 times negative 297 plus 0 because oxygen is in its natural state. And we get negative 198 kilojoules per mole. Now, this did not give us the units it should have, so I'm telling you they're in kilojoules per mole and then joules per mole Kelvin. All right, so then my delta S value, I have 2 times 257 minus 2 times 248 plus 205. When I do that math, I get negative 187 joules per mole Kelvin. Now, before I plug this in, I'm going to think about this for a second. This is exothermic because it's a negative delta H. That is favored. But this is a decrease in entropy, not spontaneity, sorry. This is a decrease in entropy, so a negative delta S, that is not favored. So if this reaction is spontaneous, it's got to be temperature dependent. So let's plug in our values. Delta G equals negative 198 minus my temperature is 25 Celsius, so that's 298 Kelvin, times, don't forget to convert to kilojoules, negative 0.187. And when I do that math, I get negative 142.3. So this is in fact negative. It was at a temperature that allowed it to be spontaneous. All right, so another example, we're looking at the decomposition of mercury to oxide. We're asked to calculate the standard free energy change, so calculate delta G. And the first way it wants us to calculate it is using the given delta G values, and then it wants us to calculate it like we did on the last slide with the heats of formation and entropy values. So here we have delta G equals products are both 0 minus reactant is negative 58.43. So I get positive 58.43 kilojoules per mole, which indicates to me that this is non-spontaneous. So now I'm going to calculate delta G using this equation, but I have to find these two values first. So delta H, products minus reactants. So again, because they're in their natural state, the products are 0, but then the reactant is negative 90.46. So I get positive 90.46 kilojoules per mole. And then delta S, products, mercury 75.9 plus 1/2 times 205.2 minus my reactant, which is 71.13, and I get 107.4 joules per mole Kelvin. Again, I know my units because they're given to me. So now I'm going to plug this in up here, 90.46 minus room temperature, also notice it's shown here as 298. And then I got to convert this to kilojoules, 0.1074. And when I do that math, I get 58.5. Whoops. That's not what I wanted. Kilojoules per mole, which is very, very close to what we got up here, as it should be. All right, last example problem, and this one kind of pulls everything together that we have been talking about. So this is an example of a free response question in thermochem that's going to pull it all together. So we're given the combustion of carbon monoxide, and the first thing it says is determine the value of delta H using the information. So we kind of have multiple tools in our toolbox right now. And so to find this delta H, the tool that we need to pull out is Hess's law. Because we're going to combine these reactions to make them add up to our overall reaction. So the first thing I see is that I'm going to have to reverse this first reaction, which makes this positive. And then once I reverse it, so I'm going to rewrite it down here. Whoops. CO plus, oh, goodness gracious. Yields C plus 1/2 O2. All right, and so then once I do that, I see that mark this out. Carbons cancel, and 1/2 of an oxygen cancels. So then I'm left with my overall carbon monoxide oops, I should have, sorry, marked this one out because I'm left with 1/2 up here. Okay, so now I'm left with my carbon monoxide plus 1/2 oxygen yields carbon dioxide. All right, so all I had to do was reverse the first one. Sorry for messing that up and making it more confusing than it is. So now I'm going to add these together. I have positive 110.5 plus negative 393.5. And that gives me negative 283.0 kilojoules per mole. So there's my delta H value. Now it asks me to calculate delta S, and I'm given the individual S or entropy values. So products minus reactants. Carbon dioxide is my product, so 213.7 minus my reactants, 197.7 minus plus 1/2 205.1. When I do that math, I'm going to get negative 86.5. Check out my units. It's joules per mole Kelvin. So now I have my delta S value. Now I'm going to calculate delta G using delta H minus T delta S, since that's what values I have. Negative 283.0 minus my temperature, 298, times my change in entropy, which is negative 86.5. Whoops. Got to convert to joules. Negative 0.0865. And I get negative 257.2 kilojoules per mole, which, because it is negative, it is spontaneous because of a negative delta G value. And since this was the favored, it was a exothermic reaction, but a decrease in entropy, this is enthalpy driven. All right, sorry for that super long lesson, but we only have one more in this unit. See you next time.